This is question 6 from the third CSAT sample paper, and in this question we're asked to show that if 8n plus 1 is a square number, then n is a triangular number, where a triangular number is a number that's the sum of all the numbers between 0 and k for some k. Okay, so if you want to have a go at this question yourself, pause the video now. Well, first let's think about what we're starting with and what we want to show. So we're starting with 8n plus 1 is a square number, and in general, when you see that, it's easiest to set it equal to m squared for some m, because then we can think about exactly what has to be true about m. And what do we want to get to? We want n to be triangular. I'll call this 1 so I can refer back to it later, and we'll work with n being triangular for now. So that means it's the sum from 0 to k, but that's not very easy to work with. We want a closed form for it, and that's fine because this is, firstly, you should know the formula for this anyway, but secondly, it's an arithmetic progression, so you could work it out from the formula for that, even if you didn't remember it. And this is a half times k plus 1. Okay, so we know this and we want to get to here. So it looks like what we want to do is to rearrange for n here, because then we'll have n equals, and we want to show it's of this form. So starting from 1, we get n is equal to, we just take away 1, divide by 8, m squared minus 1 over 8. And I want to get it to look like this. So first, I'll take out a half, and then I just have to worry about getting the rest in this form. And in general, it's easier to factorise, especially because I want two things multiplied together. So if I factorise this expression, at least I get two things multiplied together. They don't look like this yet, but we've got something to work with at least. And anyway, when you have a difference of two squares, sometimes you just factorise because there's not much else to do. So now I've got this, and I want it to be k plus 1. I have to think about how I can get there. Well, k and k plus 1 are both integers, and I'm divided by 4 at the moment, so I need to see that I can divide them by 4. And the easiest way to do that is to divide 2 into each of these. And that's because if I have two random integers, I can't be sure that either of them is divisible by 4, but we might hope that each of these things is even. How could we explain why they have to be even? We definitely need them to be even for this to work. Well, I'll call this 2 so I can come back to it later. But let's think why these have to be even. If either of them is odds, then because they differ by 2, then the other one has to be odd as well, so they're both odd. But if they're both odds, then that makes this top part odd. So we've got an odd number divided by 8, and that's not an integer. But we were told that we're basically assuming n is an integer, so that just contradicts the assumptions we're making for this question. So in order for n to be an integer, n minus 1 and n plus 1 both have to be even. So 2 has to divide n minus 1 and 2 has to divide n plus 1. And that means each of these brackets will be an integer, which is good. So we're getting closer to where we want to be. And we want one of them to be k and the other to be k plus 1. So if we make the smaller one k, we're hoping the other one will be k plus 1. But actually that's fine, because what is m plus 1 over 2? It's the same as m minus 1 over 2 plus 1. So if I make this all one fraction, I just multiply this by 2 and put it on the top, and I get m plus 1. So these are the same thing, and then that's the same as k plus 1 here. And that means I do indeed have a half times k plus 1 as required.